take me to
Funky Town?
Won't you take me to
Funky Town?
Won't you take me to
Funky Town?
Won't you take me to
Funky Town? Won't you take me down to Funky Town? Won't you take me down to Funky Town? Don't have to be beautiful to turn me on. I just need your body, baby, from dusk till dawn. You don't need experience to turn me on. You just leave it all up to me. I'm gonna show you what it's all about. You don't have to be rich to be my girl. You don't have to be cool to rule my world. Ain't no particular sign I'm more compatible with. I just want your extra time and your kiss. Oh, you got to not talk dirty, baby. And if you won't impress me, you can't be too flirty, mama. I know how to undress me. Yeah, I wanna be your fantasy. Maybe you could be mine. You just leave it all up to me. We could have a good time. Don't have to be rich to be my girl. You don't have to be cool, rule my world. Ain't no particular sign I'm more compatible with. I just want your extra time and your kiss, yes. I think we'll dance. Women and girls rule my world. I said they rule my world. At your age, mama, not your shoe size. Maybe we could do the twirl. You don't have to watch Dynasty to have an attitude. You just leave it all up to me. My love will be your food. Yeah, you don't have to be rich to be my girl. You don't have to be cool to rule my world. I'm not particular sign. I just want your extra time and your kiss.
I've been waiting for you to come back since you left Minneapolis. Snow covers the street lamps and the windowsills. The building you left Minneapolis. I wish my thoughts were pure like the driven snow, like the heavens and the springs, virgin buds. But they strangle me with their sin, fill me up with poison. Black clouds have covered up the sun again. I can always trace it back to that night in Minneapolis, here on the 7th floor, in a room I can't call mine. Deadbolt on the door, do not disturb sign. Shaking and trembling on the clean white linen, slivers of starlight danced across the ceiling. A dozen yellow roses, all that's left in Minneapolis. I wish I'd never seen your face or heard your voice. You're a bad pain in my gut, I wanna spit you out. Open up this wound again, let my blood flow red and thin into the glistening, into the whiteness, into the melting snow of Minneapolis.
Rubber ball, like I'm bouncing back to you. Rubber ball, like I'm bouncing back to you. I'm like a rubber ball, baby, that's all that I am to you.
Bouncy, 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 bouncy.
Just a rubber ball, cause you think you can be true to two.
Bouncy, 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 bouncy.
You bounce my heart around.
You don't even put her down.
And like a rubber ball, like I'm bouncing back to you. Rubber ball, like I'm bouncing back to you. If you stretch my love till it's thin enough to tear, I just stretch my arms to reach you anywhere. And like a rubber ball, I'll come bouncing back to you. Rubber ball, I'll come bouncing back to you. You bounce my heart around.
You don't even put her down.
And like a rubber ball, like I'm bouncing back to you. Rubber ball, like I'm bouncing back to you. Bouncy, 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 bouncy. I'm like a rubber band when on my shoulder you do tap.
Bouncy, 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 bouncy.
Just a rubber band because my heartstrings they just snap.
Bouncy, bouncy,
You go and squeeze me till I'm all aflame.
She calls you
like a rubber ball, like I'm bouncing back to you. 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 Rubber ball.
Well, everybody's heard about the bird. Bird, bird, bird. The bird's a winner. Well, a bird, bird, bird. Bird is a word. Well, a bird, bird, bird. Well, a bird is a word. Well, a bird, bird, bird. The bird's a winner. Well, a bird, bird, bird. Well, a bird is a word. Well, a bird, bird. The bird's a winner. Well, a bird, bird, bird. The bird's a winner. Well, a bird, bird, bird. Well, a bird is a word. Well, a bird, bird. The bird's a winner. Well, don't you know about the bird? Well, everybody knows that the bird is a word. Well, a bird. The bird's a winner with it.
Well, good afternoon, Geo Institute. As the members are still filtering in from other sessions that are running late, I think we want to keep on schedule because everybody wants to go to the party tonight. My name is Roman Ritziu. I'm at the University of Michigan, a professor there for 35 years. And I am the technical program co-chair along with Nick Hudema for this conference. And I was going to use my 3 to 5 minutes here at the beginning of this session to thank the hundreds of authors, reviewers, session chairs, and our editors of the GSPs, which are a rousing success, Roman Machnenko, James Hambleton, and Aaron Budge. And I was also going to say a few words about the work of the Technical Publications Committee, which is responsible for the quality of the geotechnical special publications. And we met well past midnight last night in planning for future GSPs and making sure that they remain the high quality that they have been up to now, and also making them worthwhile for the membership of the Geo Institute, and also making it a pleasant experience for people who are the authors, reviewers, session chairs, and so on and so forth. But I'm not going to do any of that. I'm not going to thank anybody. Instead, I was inspired by the GeoPit talks and David's talk this morning, and I decided I'm going to use my time to tell you about something that I was involved with 40 years ago, right about the time that the United States Olympic hockey team was winning their gold medal and had defeated the Russians and then the Finns. I was a junior at Drexel University in Philadelphia at that time during those Olympics, and I was dating a much younger woman. She was a freshman at the time, at a nearby college called the Philadelphia College of Textiles and Science, later to become the Philadelphia University. And on one of our dates, she said to me, "You're at Drexel. You know, we had a speaker from Drexel come to our College of Textiles and Science, and it was the most amazing talk I've ever heard. The enthusiasm, the inspiration, the organization were just overwhelming. If you ever get a chance to take a class with this fellow, I would really encourage you, even if you're not in his area." She said, "The only thing that was a little strange about him is that on top of all of this enthusiasm, he was talking about putting our textiles into the ground." 6 months later, I was taking my first class in geotechnical engineering with Bob Kerner. And it didn't take more than about 2 weeks into the class when I realized that I want to be a geotechnical engineer and I want to be a teacher. And that was exactly 40 years ago this year. So it's an important moment also for me. And it goes along with many of the things we heard this morning about the Geo Institute being a family and the traditions that we carry on, the inspiration we give to our students. And Bob, of course, will be sorely missed. When he passed away, I instinctively went to my notes from my very first classes, and there it was on the very first day of classes. The things that I'm still using in my research today, looking at intrinsic properties of soils and how they affect soil fabric and how they affect mechanical properties and hydrologic properties, back before Bob was even involved in geosynthetics. And 40 years later, I'm actually about to celebrate my 40th anniversary with that date I had who encouraged me to take a class with Bob Kerner. So with that, I'm going to introduce our first speaker, Mario Ruel, President of the Canadian Geotechnical Society, and he'll say a few words. Oh, before I bring him up here, I'll also mention, so I don't come back up here, that we have two GeoPit talks coming up right after Mario, and it's going to be Vanessa Bateman from the United States Army Corps of Engineers and Victoria Bennett for Rensselaer Polytechnic Institute.
Thank you. Good afternoon, bon après-midi. Thanks to Derek and Brad for inviting me to say a few words for the Canadian Geotechnical Society. By the way, congratulations for an excellent start. The last few days have been great. I enjoyed today with the dynamic start with the GeoPit talk. This is a really good idea. The CGS is really proud to be partnering with the Geo Congress 2020 in the Great White North. We, the Canadians, are really happy when it's cold, and I'm glad here to represent a big bunch of Canadian delegation in the audience. Whoever are here, so we're happy to be here. Over the past few years, we have developed a good collaboration, closer collaboration, and then closer ties, so we're really eager to continue this and continue to get organized together and get some synergy with our mutual organizations. And now to finish, just a few things from north of the border, a couple of announcements. In the audience here, we have Rob Kenyon and Ken Scatfield in our executive committee that are working on updating the Canadian Foundation Engineering Manual. So the last update was in 2006, and we're about to come up with the new manual. So for those of you who are using this from time to time, it's going to be available next year. Rob, is that it? Yes, it is. And lastly, I'll finish with this. We invite you to Geo Calgary, to our big party in Geo Calgary in mid-September this year. I say party, no, it's an annual conference, but we like having fun while learning a few things, networking, and having a big party. So we'll see you, hopefully, all in Calgary mid-September. Thank you.
All right, good evening. So back to our pit talks. I hope you don't mind if I wander around on the stage a little bit. I'm not very good at standing still. So I have a question for you this evening. Have you ever noticed how life and your career never really quite unfolds the way you expected? Anybody here doing exactly what they thought they were going to be doing when they were in high school? Please raise your hand. Ah, we got one. Very good. All right. You start out when you're young imagining a million possibilities, right? What do I want to be when I grow up? And it changes daily, monthly. Astronaut, teacher, musician, writer. Like a lot of kids, I went through all of these, although I thought astronaut was way cooler. And I planned for each of these careers, right? What I would need to do in high school, what kinds of classes would I need to take, what college would I need to attend. And never mind, there we go. And if you told me I was going to be doing this in high school or even the first part of college, I don't think I would have believed you. I didn't even start out college as an engineer. And I have to admit, I spent a good bit of my childhood thinking that I did want to be an engineer, so there's a funny little part of this story, except my 4th grade teacher burst my bubble completely when she didn't want to talk about driving trains when we were talking about engineering in math class. Yeah, I really did think for a while. So I know that life can be a little unexpected, and I ended up becoming a geologist and later an engineer. So, and I was really surprised, though, when I ran across a speech by former President Dwight Eisenhower in 1957, and he said something that I think is relevant to us today within our profession. And he said in this big speech to some national defense folks, plans are worthless. It's a big statement for engineers, right? Plans are worthless. This guy right here, when he went to the beach, he thought he was going to swimming. He thought he was going to have a nice, good time, jumping around in the water, and it turns out he got slapped in the face with a wave, just in time for his mom to capture a picture. But the other part of what he said was planning is everything, and that's a very interesting dichotomy. Plans are worthless, but planning is everything. This guy's not in over his head. He has survived the wave coming past, and he's ready to move on and deal with the next challenge. And he says in the speech, there's a great distinction when you're planning for an emergency, because you have to start with the very definition of emergency, which means you don't know exactly how it's going to happen. It's unexpected. That's why we call it an emergency. And it's certainly true of rock engineering and geohazards in general, right? We know they can occur. We've got a lot of math. We do a lot of modeling. We know the circumstances where they're likely to occur. But the exact timing is a little more of a problem, isn't it? Certainly our nice, now destroyed rockfall sign, they had an awareness that they had this hazard here, but nobody seemed to know exactly when that rock was going to come down. Which is why one Sunday when I thought I would be attending a Boy Scout breakfast, I ended up on top of a rock, as seems to happen a lot in my career, dealing with a toppling failure. And so it rained. I wasn't surprised to get the phone call, although I was definitely surprised not to get to eat my bacon. But it struck me as I was thinking about this speech that you learn a lot from this kind of a dichotomy, this tension he was talking about between plans and planning, doing this kind of work. Plans are useless, but planning is everything. After all, some of the best rock drains I ever designed started out as rock bolt holes. We drilled them for an entirely different reason, and the hole decided to make water and continue to make water. And so you could say, oh, I'm determined this bolt's going to go right here and deal with the water problem, or you can say, you know, I really did need some drains. I think I'm going to make a new bolt hole over here and let this thing drain and let this one make water. The essence of the observational method, of course, is to look what's happening while you are doing something and react to it. We know emergencies don't happen exactly the way we plan. One of the things that I don't think we think about enough as a profession, though, is what happens when one common driver affects a wide variety of infrastructure at the same time. Now, I know a lot of you probably heard about the 2010 flood in Nashville, although we complained for a while that CNN and everybody else seemed to forget about us. This is Old Hickory Dam. This is upstream of Nashville, and as you can see, that's rather full. It was a big storm. It caused a lot of flooding in the Nashville area. You might have seen some of the pictures of downtown Nashville or the Ryman or the Opryland Hotel. But one of the things that you didn't hear on the news about this rain event is that we had hundreds, literally, of landslides and rockfalls in the entire Middle Tennessee area as a result of that exact same storm. So now you have a city that has flooding issues to deal with, scour issues to deal with, roads that have been washed out, and roads that have been taken out by landslides and blocked by rockfall. So this is something that I think we really need to pay some time to. Some of these turned out to be quite large. Not all of them were small. And that brings us to this word, risk. We use it a lot, right? You hear it in a lot of presentations, risk. We talk about it. And we have to understand with our work how our projects can fail, under what circumstances, because it is fundamental, absolutely fundamental to good design and to developing resiliency within our infrastructure. We look at the probability of failure. What's going to happen, maybe? How likely is it to happen? And what are the consequences of that? Because not learning these lessons from previous projects can be catastrophic, right? You don't want to repeat mistakes of the past, even if it was not foreseeable at the time. You've got to learn from these failures to take these lessons forward. We don't want lock walls collapsing inward and killing workers in the middle of an excavation. This is not how we want to see things happening. And so we design with these kinds of potential failures in mind. It's the essence of what the Corps and many others call risk-informed design, right? The idea that understanding your potential risks improves your design, improves your safety, improves the ability for you to design and monitor your projects in such a way that you can address these issues and deal with some of the challenges that may be ahead. It's also why long-term monitoring, emergency action plans, and risk assessments are so important, because that's that piece, that's that planning piece that we were talking about earlier, when the difference between plans and planning. And it has something else here. It helps you develop your judgment. The judgment that you need to address these kinds of risks and to handle emergencies starts right here with planning. With relentless preparation and study. It's not enough to finish in school, right? It's great. You got a nice shiny degree, you graduate, you walk out into the world, you take your PE exam. Oh, great, I'm a PE, awesome. You're not done. You're never done. Because as former President Eisenhower remarked later in his speech, if you haven't been planning, you can't start work intelligently. Oh, and that's the reason it's so important to plan, because it keeps you steeped in the character of the problem you may be one day called upon to solve. Again, relatively profound. He was talking about national security, but it's got rather a lot to say in our area as well. So where does judgment come from, right? This is a question that we have been asking ourselves in our profession for some time. Well, certainly it comes from experience, yes. And as Dr. Marr quipped in a recent presentation, it also comes from bad judgment, right? Learning from the mistakes of the past. But I think we develop part of the judgment that we need because of this fundamental dichotomy, this knowledge that we cannot define everything, that we are going to have to deal with the unexpected during construction, during long-term monitoring, dealing with our infrastructure. We have a dynamic situation that we have to cope with. Failures are uncomfortable. We don't like to talk about them, at least when they're ours, right? It's a lot easier to talk about somebody else's failure than your own. But they are one of the most important teachers that we will have and the most important guides to better judgment. And so we must always be looking at these kinds of risks to our plans. How likely are these drivers to happen? We have to consider this in our designs as a whole. How will our infrastructure react to problems that we may not be able to control, right? To forces that we may simply have no control over. And how are we going to design for that? Do we design for that? How much do we design for it? How big do we build it? How much resiliency, you've heard that word a lot, right, do we put into the system? These are big questions, and they are not cookie cutter. They are not textbooks. They are the judgment that we have to be performing every day as we are doing our design. And not only is it necessary that we design this, the bridge, the flood wall, the levee, the rock slope. It is important that we consider the overall infrastructure as a whole and how it's working together as a system, because it is vitally important for us to consider what second-order effects of one particular piece of infrastructure failing at the same time that another one does, if they can fail by the same drivers. So we work in one of the best professions there is, honestly. It has been my great privilege to have been working in this for as long as I have, and I hope to continue to work into it for many more years. And as we saw from our opening session, and as I hope you are aware, we really, truly do stand on the shoulders of giants. If we have seen further, as the quote goes, that is why. But it behooves us to build on that legacy, to continue to strive, to push, to understand these risks that we can face with our infrastructure. We understand the threats to our infrastructure, understand how that infrastructure can fail, understand how we can design better and monitor better. We have to keep striving to refine our understanding because our society and our world depends on us to get it right. They really do. And if you'll pardon a final moment of humor, from a geo who really, really loves rock engineering, and after many, many times that I have walked out onto a rock cut or walked out into a site and saw someone doing something that really made me nervous, I would like to leave you with one final thought. Please do not park here. Thank you.
Good evening. My name is Victoria Bennett. I'm a professor at RPI, and tonight I'm asking the question, is the road to learning engineering judgment a virtual one? And when I first set the title for this talk, I asked with my collaborators listed here whether they liked this title, that they thought this was a good title, and I had originally said, is the road to teaching engineering judgment a virtual one? And the overwhelming response among the group was that it has to be learning because students are at the center of this. And hopefully that comes through as you see what we're talking about here. But following along the road analogy, this idyllic picture from campus is of a road, a local road just below one of our buildings, the building that I teach in. And I often bring my students out to this site, and you can see that it doesn't look so idyllic in this picture. And I think that engineering judgment really plays into what you see here. And even if you don't want to spend time teaching your students or hoping that your students learn engineering judgment, those of us who do report to ABET in the room will have to find a way to assess that. And that's what I'm showing here as part of the new criterion for ABET. So just previously I heard from Scott Brandenburg that being the ABET coordinator is not a job that anybody should take on, and it is my new job in our department, but I'm hoping that what you see through the work that we're doing at RPI, that we might have a tool that allows you to assess engineering judgment in your students, even if you don't necessarily know how to do that yet. The next piece is about learning, really. And so maybe all of us could close our eyes and think back to a time where we had an impactful moment in a classroom. And for me, it was in my earth science class with Mr. Kenzel, and he would make this face where he was imitating students taking a Scantron exam with their pressing the pencil so hard that they rip through the page and their tongue sticking out, and that is burned in my memory as an impactful learning moment. So maybe there's these special times and special things that we can do in the classroom to really make an impact on our student, engage them in our topic, in geotechnical engineering in this case. And maybe the way to do that is through educational games. So if I think of educational games, I think of this. And I'm just hoping that there's a few of you in the audience that are of my era that know that this is from the Oregon Trail game. And actually, to come full circle, the Minnesota Educational Computing Consortium in 1974 produced the Oregon Trail game. So 1974 doesn't speak to when I was in school, but it was still around in the 90s. And asking my students what do they think of when they think of educational games, maybe this resonates a little bit more with the younger folks in the room. But I want to speak to an educational game that we're working on at RPI. Educational games have been around for a while, and obviously some leave lasting impressions on our personal educational journeys. I'd like to think that perhaps GeoExplorer is part of the future of educational games. GeoExplorer was developed through NSF funding and collaboration between researchers at RPI, Northeastern, Southern Methodist University, Broad-Based Knowledge, Cal State Fullerton, and Manhattan College. The important tenets of this game were to provide practical field experience to undergraduate geotechnical engineering students and build in assessment of their performance within this virtual space. Teaching engineering judgment is a gap in our current pedagogy. Now, as we travel on this virtual road, let's see if perhaps this is a way to teach engineering judgment. We are arriving at a field site where students can conduct a CPT. The CPT exercise is part of an exciting new mixed reality experience to integrate field testing and practical experience into the existing civil engineering curricula. Students have the opportunity to conduct a CPT at 4 different field sites Part of what enhances this experience is the inclusion of the mobile phone in the bottom right portion of the screen. As students are completing tasks in the virtual environment, they are receiving messages from their boss with specific instructions about each particular field site. Through the designed variability in the 4 field sites, students are able to apply what they have learned in lectures to real virtual scenarios. The mobile phone is also used as an assessment tool. The messaging that appears on the screen are questions that in previous educational research would likely have been included as a survey or in-class assignment. This built-in assessment tool allows us to gather information about the student's knowledge and confidence related to CPT in a sneaky way, simply as a conversation with the boss. As we begin to collect CPT data, you will hopefully see this is further opportunity for students to learn through doing. Students must select the speed to advance the cone, use manual advancement for the first few meters before setting the test to automatic. As the cone advances, students must monitor the tip-resistant values and inclination angle. The stopping depth is selected by the student and speaks to their own judgment based on the instructions from the boss. For each site, students are asked to interpret their collected data and report back to the boss about the soil type encountered at a relevant depth. The student selection is recorded along with other gameplay data, such as how long they spent on certain tasks. A valuable feature of this CPT environment is the ability for students to fail with a safety net. As you saw there, one student said, "My boss is going to be mad." We have big plans for the future of this virtual environment. Everything you have seen so far already exists and has been implemented on 4 campuses for over 500 undergraduate students. What you're seeing now is the game called Levee Patroller, developed by Casper Harteveld, now at Northeastern University. This game was used to train civilians in the Netherlands to inspect levees and report concerning indicators. During Casper's PhD research at TU Delft, he was able to show that civilian game players performed as well as experts in recognizing critical failure features in virtual levees. We will combine the previous Levee Patroller assets into the GeoExplorer space. In this new robust GeoExplorer game, we will provide lots of opportunities for students to practice engineering judgment, and through the built-in reporting feature, we may also have an automatic assessment of their applied judgments. The mixed reality piece of this project is currently realized through the use of a mock internship experience with the fictitious company Terra. Students apply for a position on the Terra website and receive an email with their welcome package and instructions to complete assignments within the virtual environment. This internship experience will be expanded to now include levee inspection and design. Our vision is to use a traditional classroom assignment and established geotechnical software packages to produce designs that are then incorporated into the virtual environment. Students will enter the virtual environment and be able to see their designs perform under extreme loading conditions. As we watch the progress of this levee failure, we can think about the impact of this learning through failure's opportunity that it may have on our students. In the virtual environment, students will be able to repair failed sections and reflect on what went wrong with their original design. In the next few years, GeoExplorer will be a mixed reality experience where students collect virtual CPT data, supplement it with real lab tests conducted as part of their existing coursework, use traditional software to produce designs that are built in the virtual environment, and tested under a variety of loading conditions. Perhaps this is where the future of educational games is heading. And maybe this is what students years from now, when they think of educational games and what might have been an impactful moment in a classroom for them, perhaps this is the impression that they will leave with. I was expressly forbidden to do a live playing of the game, so thank you very much for indulging the video portion. These schools that you see here are committed to implementing this new GeoExplorer experience on their campuses, including both the CPT module and the levy inspection and design module. So I leave you with the question, again, is the road to learning engineering judgment a virtual one? And let you keep this picture in your mind so that in the future, when students think about GeoExplorer and think about how to develop their engineering judgment, perhaps this is also what you'll think of. I want to give big, huge thanks to the students at RPI. These are not the RPI students, these are my kids. But the RPI students, 3 out of the 4 listed there, and the RPI team who just won the GeoWall competition, so kudos to them. Also to my mom who came to this conference to watch my 5-month-old baby so I could give this talk. Thank you so much.
Good evening, everyone. My name is Joe Cavanaugh. I'm the Vice President of Technology at Tensar. How's the clicker work? Obviously not the vice president of this technology. Coming through? Great, okay. So Dr. Brian Mercer was a prolific inventor. He invented numerous products, process technologies, including Tensar geogrids and Netlon drainage nets. He was the founder and for many years the leader of the Tensar and Netlon companies that developed and commercialized these products globally. These products are now used in a wide range of civil and geotechnical engineering applications, and these products continue to be researched, evolved, improved, following the R&D culture created by Dr. Mercer. Dr. Mercer was a true visionary and strongly believed in and supported cooperative research and the advancement of science. Despite being a materials and mechanical engineer, he recognized the need to focus on application research of these polymeric materials that he had created, in particular civil and geotechnical engineering applications. The Mercer Lecture Series was established in 1992 in honor of Dr. Mercer. The objective of the series is to recognize individuals that have made significant technical contributions to the advancements of geosynthetics and to provide an opportunity to present their work at numerous conferences around the world. I'm honored to be here tonight to introduce the current Mercer lecturer, Dr. Carrie Rowe from Queen's University in Kingston, Canada. If you could advance to the next one, please. Over the past 45 years, Dr. Rowe has gained extensive experience, extensive research and consulting experience in geotechnical, hydrogeological, geosynthetics, soil reinforcements, and geoenvironmental engineering. His work has won numerous awards, and he has been appointed to the world's most prestigious scientific and engineering societies. He has given numerous distinguished lectures, including the IGS Giroux, BGA Rankin, ISSMGE Casa Grande, and the ASCE Carl Terzaghi lectures. In 2013, the ISSMGE created the R. Carrie Rowe Lecture. Dr. Rowe truly qualifies as a geosynthetic pioneer and legend, and again, I'm honored to be here tonight to introduce him. His lecture tonight focuses on one of the original and most fundamental applications of geosynthetics, aiding in the construction on soft soils, Please join me in welcoming Dr. Carey Rowe.
Well, thank you, Joe. Those two last talks, wow, they're a hard act to follow. What I would like to do to begin is acknowledge three former PhD students, Kaiwan Liu, Dan, and Louis King, who helped me put together this presentation. Many others have contributed to the research I'll talk about, and they'll be acknowledged at the appropriate time with references as we work through this. I'd also like to join Joe in acknowledging the key role that Brian Mercer played in developing the modern geogrid, which has many applications in the talk I'm going to be giving this evening. It seems that today is a day of 40-year reminiscences. And what I would like to do over the rest of this talk is have you join me on a 40-year exploration of the role of geosynthetic reinforcement in allowing us to build embankments on soft and difficult soils. At the end of this presentation, I'd like to leave you with three key points. Firstly, it has now been very well established over decades that geosynthetic reinforcement is a very cost-effective means of building or augmenting the soil behavior in constructing over very difficult soils. In designing and constructing embankments on soft soil, reinforcement can play a very key role, and so it's essential to understand the properties and characteristics of that reinforcement if we're going to have good long-term performance. However, reinforcement is not magical. It has never been to Hogwarts. It is never delivered with a wand or skyhooks. And like every other engineering material, for it to be effective, it must be incorporated in an appropriate design. Thirdly, while the properties and the characteristics of the geosynthetics are critical, we mustn't get so absorbed in the geosynthetics that we forget the soil mechanics, which is equally important to ensuring good long-term performance. My topics that I'm going to cover tonight start off fairly simple with some basic concepts and build up fairly quickly to the more complex, leading me to, with one of the hot topics of today at the very end, column-supported embankments. And we're going to look at how 40 years of knowledge built into that. But let me begin where I began 40 years ago, with brown and not grey hair, building embankments with reinforcement on fibrous peat. For those of you not so familiar with fibrous peat, it's usually submerged and has a very low submerged unit weight, and so the initial effective stresses in the soil are very low. Its strength is pretty well defined by a more Coulomb failure surface, where the cohesion intercept reflects the tensile strength of the fibers, and the frictional component depends, of course, on the effective stress, and a friction angle typically about 27 degrees. So if we want to construct over this peat deposit, we need to get significant pore pressure dissipation during construction so that we can mobilize some of that strength. Now, in that, we need to consider the pore pressures relative to the applied stress, and we need to control the pore pressures so they do not exceed a reasonable value. Even with that, it's a challenge to build over peat. And so here was our first objective, to build a 1 to 1.5 metre embankment above grade. And we had a number of instrumented sections, but the most challenging was over 6.9 metres of fibrous peat underlain by sand. And for the time, we used a very strong multi-filament geotextile with an ultimate tensile strength of 180 kilonewtons per metre, a secant stiffness of 850 kilonewtons per metre, and a break strain of 25%. This was the first time in Ontario this had ever been attempted. The embankment was constructed in 3 stages. We're going to talk about 2 of them. In the first stage, 2.74 metres of fill was placed, and at the end of the fill placement, there was 2.6 metres of settlement. But the reinforcement was working and had developed a strain of 5%. It was then left for 8 months to allow pore pressure dissipation. And when we came back at the end of 8 months, our 2.74 metres of fill had given rise to 3.1 metres of settlement. And since the water table is at the ground surface, this meant that portion of the road was now submerged, as we see here. But as those pore pressures dissipated, the peat gained strength. And as it gained strength, the reinforcement became less critical. And so the strain in the reinforcement decreased from 5 to 2%. We now add additional fill to bring the fill to 5.9 metres. And at the end of its placement, we've got 4.2 metres of settlement. And the strain in the reinforcement is 11.5%, well below the failure strain. It's now left for 2 years to allow pore pressures to dissipate. And after the end of that 2 years, before the final finishing steps, our 5.9 metres have got us 1.1 metre above original ground level. And the strain in the reinforcements dropped from 11.5 to 8%. Now, this is fairly typical of what you get on a traditional soil where the peak pore pressure is reached either during or at the end of construction, and after that, as excess pore pressures dissipate, the soil gains strength and the reinforcement becomes less critical and the strain reduces. So here the high modulus geotextile reduced lateral movements and increased stability, but it didn't come with skyhooks. If you're going to get large consolidation settlements without the reinforcement, you're still going to get them with the reinforcement. Control of pore pressures was critical, and they were kept to about 1/3 or less of the total stress generating them. And effective deformation and strength parameters together with pore pressures provide very good predictions of what was going to happen. Here is a second embankment with much less peat, less than 2 metres, but even more challenging in ways because it's underlain by very soft organic silt with a very low shear strength below the peat. The silt itself was underlain by a good sand layer. Again, we want to get 1.3 to 1.7 metres above grade, and here a polypropylene biaxial geogrid was used. You can see the geogrid on top of the peat deposit, and as the embankment advances towards this location, there's also a tension crack just formed in the peat. Here we see the embankment being advanced towards a monitoring section. And what do we find from this? Well, firstly, again, the rate of construction control was critical to short stone stability. Everything was good if you kept below about 38% of the total stress. But at one point, the contractor got a little too exuberant, piled the soil too high, pore pressures went to 70% of total stress, and a failure occurred, reinforcing the importance of controlling pore pressures during construction. Now, with case histories like this and calibrated numerical models, you can come up with design guidelines, such as the one you see here, where for a given height of soil above grade and unit weight, you can calculate what stiffness of reinforcement. So strength is, yes, it's important, but stiffness is critical to many of these applications. So if we wanted a stress of 30 kPa at ground level, and the peat were 3 meters thick, we only need a very low stiffness reinforcement. At 5, we need about 400 kilonewtons per meter. For 8 meters, we need about 800 kilonewtons per meter to carry the weight of the soil below the ground level. Now, that was the case on a firm foundation, but similar design recommendations and charts were developed with a soft soil beneath it. Now, that's a case where we're looking at partial dissipation of pore pressures during construction. Now let's go to undrained construction. So here is a 3.3 meter thick organic clay with an undrained strength around 8 kilopascals. And to perform the first embankment construction, soil was excavated to create a trench and used to form a retaining bank. Then hydraulic fill was placed until failure occurred. And it occurred at a fill height of 1.75 meters. At a second section, a layer of relatively high strength reinforcement was placed on top of the organic clay. And then the trench was excavated, the retaining bank of excavated soil put on top of it, and the hydraulic fill placed until failure occurred at a height of 2.75 meters. That's 60% higher, so it definitely shows a significant benefit of the reinforcement. Now, if we do a finite element analysis of the unreinforced embankment, it tells us more or less the same thing as limit equilibrium. It shows you that at the failure height, we have uncontained plasticity and a failure mechanism that passes tangent to the base and through the toe. But what limit equilibrium doesn't tell us is what is happening in the reinforced case. So here at 1.8 meters, we have contained plasticity because the reinforcement is carrying some of the load that would otherwise be transferred to the soil. But by 2.05 meters, we have uncontained plasticity. And all that's holding the embankment together from here on is the reinforcement. So if the reinforcement is doing work, it must be experiencing strain. So let us investigate the change in strain as the embankment fill height increases. And you can see both the calculated and observed strains are minimal until we reach an embankment height of about 1 meter. Why? Because the soil is still elastic and it is doing all the work. The reinforcement's not needed. But as we go from 1 to 2.05 meters, now plasticity develops, and at the end of 2.5 meters, we have contiguous plasticity, and the reinforcement is becoming critical. You can see the rapid increase in strain as we approached 2 meters. Now, 2 meters is roughly the design height with a factor of safety of 1.3. So this is typical of many design applications in traditional soils where at the end of construction the pore pressures are going to dissipate. We need the reinforcement to give us our factor of safety, but the strains in the reinforcement are quite small. It's there in case we got the strength a little wrong. Now, if we go a little higher, now the strains really develop quickly until failure occurred. And in this case, they occurred at a strain of 3.3%. That is about a third of the strength of this material, a third of the break strain. So why did it occur? because of insufficient anchorage. The reinforcement pulled out between the organic soil above it and below it. So we've now explored traditional soils with partial pore pressure dissipation, undrained. There are often situations with traditional soils where we need, for clay, some pore pressure dissipation during construction. And here, prefabricated vertical drains, or PVDs, become quite critical to a cost-effective means of reducing pore pressures. They've been around for 30-odd years, very effective, and a very nice case that describes their effectiveness, published in 2017, looks at 4 dikes, heights of 5 to 11 metres on a soft clay, tensile reinforcement, PVDs, and shows that in these cases neither reinforcement nor PVDs alone were sufficient. But their combined use increased the safety factor by 50 to 70%. The reinforcement increased stability and allowed more fill to be placed for consolidation. The PVCs accelerated the consolidation process, but again the reinforcement did very little to manage consolidation settlements. But the PVDs did provide for much more rapid pore pressure dissipation and hence strength gain. So let's explore the effect of the stiffness of the reinforcement in a situation such as this. So we're plotting on the left-hand axis the net embankment height, which is fill thickness minus maximum settlement, versus the embankment fill thickness. And for this set of parameters, with a construction rate of about 2 metres per month and drains at 2 metre spacing, unreinforced we can get about 2 metres above grade. 250 kilonewtons doesn't do very much. At 500 kilonewtons stiffness, we're up to about 3 metres. At 1,000, we're about 4, but large settlements. And at 2,000 kilonewtons per metre, we can get up to about 6, with a fair bit of settlement. Of course, one of the benefits of the pore pressure dissipation is an increase in the undrained shear strength along a potential failure surface. This soil had 5 kPa at the surface initially, and so beneath the shoulder a 5 kPa increase is rather significant. And you can see that the increase decreases with the effective stress as we move towards the toe. Now, these have all been on fairly traditional clays or soils where the pore pressures reach a maximum during or at the end of construction. Let's now turn our attention to rate-sensitive soils. And you could certainly argue that all clays are rate-sensitive, and you'd be right. But what we're going to be particularly interested in is highly rate-sensitive soils where the maximum excess pore pressure is not reached at the end of construction, where in fact the pore pressures continue to build up after the end of construction. In 31 cases looked at by Crooks et al. In 1984, a third of them fit this category. And this has been a particular challenge in the province of New Brunswick in Canada, where the Department of Transportation had an embarrassing situation where embankments were failing after the end of construction. To try and see how reinforcement could address that problem, we got to build 2 test embankments to failure, one with and one without reinforcement. We only have time for the second tonight. Now, this is a rate-sensitive soil. The properties are there. I won't go through them, other than to highlight for you the liquidity index, which is around 1, from 1 to 6 metres depth. And that is fairly characteristic of these highly rate-sensitive soils. a reasonably high liquidity index. This embankment, the reinforced one, was built with a relatively strong geosynthetic reinforcement with a failure strain of 13%. And it was successfully constructed to 8.2 meters and left. And it sat there for a while. But as it sat there, the pore pressures increased. As the pore pressures increased, the effective stress decreased. As the effective stress decreased, the strain in the reinforcement increased. And it increased until the reinforcement failed at a strain of 13%. And then the instrumented point you can see at the toe rose up about 2 meters above its original level as the failure occurred. So this is a viscous type failure after the end of construction due to creep and destructurization of the foundation soil. The deformations, the creep and destructurization leads to excess pore pressures increasing and a decrease in shear strength. The field vane, even when you apply typical corrections based on plasticity index, overestimated the actual mobilized soil strength at failure. And when one compares the unreinforced and the reinforced sections, the reinforcement significantly increased the failure height, and at a given failure height, reduced the amount of viscoplastic deformation. So taking this soil and doing a numerical experiment to the design height based on traditional limit equilibrium calculations, using the vane strength with typical correction, a factor of safety of 1.3, and a typical allowable design strain of 5%. And now we're going to numerically build on the same soil profile that we had for the Sackville embankment to a design height of 6.75 meters. And we're going to plot the largest strain in the reinforcement versus time. You can see it starts off with very small strains because the soil is initially elastic and doing the work. But as plasticity, and particularly viscoplasticity, develops, the strains increase quite rapidly. And after 500 hours, we've reached our 5% design strain. At the end of construction, we're not much higher, about 6%. Now, if this was a traditional soil and the pore pressures dissipated, everything would be fine. But it's not. And the pore pressures keep on going up. And this reinforcement would typically fail between about 11.5% and 13% break strain. If that's the case, then it would fail between 12 and 21 days after the end of construction. But if the reinforcement could sustain a strain of 16% or more, then ultimately everything would be okay. But it shows us that we have to consider the viscoplastic behavior of these rate-sensitive soils, together with the reinforcement, and assess what is a suitable mobilized strength for the design. I don't have the time to go into the details of that, but anybody interested can refer to our paper. And I now want to add one extra level of complexity, the viscosity of the geosynthetic. Up to now, we've assumed elastic reinforcement. For many geosynthetics, that's not a reasonable assumption. Here are two different products, not necessarily the one shown in the picture on the right. And we're looking at reinforcement strain changing over time under a sustained load of 30% of the ultimate strength. And you can clearly see viscoelastic performance in the reinforcement. So how does this affect the overall performance? So going back to plotting the net fill height versus the, in this case, design strain, the long-term design strain, for a rate-sensitive reinforcement and a rate of construction of 10 metres per month. If our allowable mobilised strain was 3%, we could get to 2.9 metres fill height above original grade. If it was 5%, we could get 5% higher at a little over 3 metres. Now, what if we change the rate of construction? Because we're dealing with two rate-dependent materials here, the soil and the reinforcement. So if we reduce the rate of construction to 1 metre per month, keep the same reinforcement, then for a 3% allowable strain, we get a 7% increase. And if we go to 5% and keep the original rate of construction, but change the reinforcement to a less rate-sensitive geogrid, the one I showed you in the picture before, here we see a benefit of about 12%. So simply the choice of product that we used made a notable difference in terms of its creep performance. Again, I don't have time to go into the details, but anybody intrigued can read the paper. And this is going to lead me into much more recent topics of column-supported embankments. And we're going to begin looking at floating column-supported embankments, firstly without and with geosynthetic reinforcement. So the scenario we're looking at is shown here. We've got columns or piles. They could be deep mixed columns. They could be concrete piles. Floating in the soft soil, we have potentially a layer of reinforcement. We have a load transfer platform, usually of a coarser granular material, and then we have the embankment fill itself. And a case published in 2012 and analysed in 2015 looked at 3 field constructions. We only have time to talk about 2 tonight. S2 was a unreinforced pile-supported embankment, and S3 was a reinforced pile-supported embankment on the same deposit. And in the case of the unreinforced embankment, the settlement of the subsoil between the piles was around 130 millimetres for the loading conditions, while at the pile head it was only about 10 millimetres, leading to a differential of around 120 millimetres, which will propagate towards the surface of the embankment. If we had the reinforcement, we get a much better distribution of the load. Load is transferred from the soil between the piles to the pile head. And as a consequence, we get less settlement of the soil between the piles, around 80 millimetres in this case, and more settlement of the pile head, around 30 millimetres, reducing the differential to about 47 millimetres. So the choice of reinforcement and its addition is important. Now, what can we do with prefabricated vertical drains? Here we've got some deep mix columns, and at the centroid between them we have a prefabricated vertical drain. We're looking at a cross-section, and we're going to focus, because of time, just on 2 points. One at the bottom level or elevation of the columns, and we're going to look at the pore pressures, and the other at the top of the crest, the embankment, and we'll look at settlement. So starting with pore pressures at point A, if we had a plot of excess pore pressure at this location without PVDs, we get the curve in yellow. And you can see at the end of construction we're about 85 kilopascals. And after 3 months, it's dropped to about 68. And it takes about 7 years to get 99% degree of consolidation. If we put in the PVDs, this particular case, it didn't make that much difference to the end of construction pore pressures. But it made an enormous difference to the rate of dissipation. So after 3 months, we're down to 23 kilopascals, and it's pretty well over by a year. Now, what does this mean for settlement? It actually means quite a lot. If we look at the maximum settlement at the center line without PVDs, we get almost 60 millimeters, and it takes around 7 years. With the PVDs, we reduce the settlement by about 30%. Because we've allowed more strength gain, we've reduced plastic deformations in the foundation, and therefore less settlement. And it's over in terms of consolidation, primary consolidation in a year. Now, what about the viscosity of the reinforcement? Here we're going to look at both a viscous foundation and viscous reinforcement. So we're back to the same soil profile that we looked before. We have no PVDs in this case. We've got the same design height as we looked at before, 6.35 meters. We've got a construction rate of 10 meters per month. But we do have the columns that we didn't have before. So that changes the problem quite considerably. We've got the same reinforcement. We've got a G1, which is a grid, fairly rate sensitive. And at the end of construction, we've mobilized about 4.5% strain. If the pore pressure is dissipated from this point on, everything would be sweet. But because it's a rate-sensitive soil with destructurization, the pore pressures build up. The strength of the soil goes down, and the strain in the geomembrane, in the geogrid goes up. How much of that is due to the viscous behavior of the reinforcement? Well, let's analyze it with the same elastic stiffness as the reinforcement had at the end of construction for the geogrid. And then we look at the two, and we can see that the difference, the greater strain in the case of the viscoelastic reinforcement, is due to creep. If we did a pure creep test at the load applied at the end of construction, this is what we'd predict. So clearly it's an interaction between the creep of the reinforcement and a creep and the pore pressure buildup in the soil that are resulting in this much higher strain. Now we get a higher strain due to creep. What happens to the forces in the reinforcement? So this is exactly the same problem, but we're looking at force instead of strain. And if we did it for the elastic case with the same stiffness at the end of construction, we would have a force of just around 60 kilonewtons per meter at the end of construction, increasing to about 95 kilonewtons per meter. If we have the viscous reinforcement, it again increases but less because of relaxation. We're getting more strain but less force due to relaxation in the reinforcement. And if we were just to hold the load constant at what it was at the end of construction, the reinforcement would lose the stress you see in this diagram due to relaxation. So we both an increase in strain and a decrease in force in the reinforcement due to relaxation. So stress relaxation tests or creep tests provide very useful information for input into appropriate numerical models, but they don't tell us what's going to happen in the interaction problem. So this brings me to the last topic I'm going to touch on. I've gone a little faster because I know we're running late, But I do want to spend a few minutes on end-bearing column-supported embankments. It looks very much like what we were just looking about, except that now we have end-bearing columns or piles in a firm stratum. I'm highlighting this because I'm interested in long-term serviceability. As editor of Geotextiles and Geomembranes, about 20% of the papers I receive each year is on this topic. Despite that, it is not well understood, and many design methods are severely lacking. If we think about what's happening in this case, we have a reinforcement which to work must deform. And so if we're looking at the head of the column, we have a load A from the area of influence above the column head, and a load B which is being transferred to the pile from the soil between the piles. So the total load carried by the pile is A plus B. If we now go between the piles, we have a contributory load B plus C. Part of that load B is carried by membrane action through the reinforcement to the pile, and load C remains on the soil to cause deformation of that soil. Now, in dealing with these problems, soil arching is absolutely critical, and as Tetsagi said back in 1943, arching is one of the most universal phenomena encountered in soils in both the field and the laboratory. Many of the existing models assume the shape of a failure surface with soil arching. Many assume failure surfaces lack any sound theoretical basis. They're based on empirical data for a limited range of test conditions. And while it may apply to those test conditions, the shape is being generalized far too much. Soil arching is a deformation-dependent process. The deformation that is critical here is described by the reinforcement sag. Now, under certain conditions, you can get a good agreement between what you're going to predict with the design method and what you observe, but only if you have strain compatibility. Are you going to have strain compatibility in the long run? Serviceability-based design really needs to depend on the time-dependent coupled arching stress reinforcement deformation behaviour. That's a mouthful because it is complex. It builds upon all of the things we've been talking about today and more. We can see that if we look at a ground reaction curve. So we're looking at a plot of the stress reduction ratio. That's the reduction in stress on the subgrade between the piles versus the relative displacement between the pile and the soil. And we see that at relatively little displacement, about 1%, we've already mobilized a lot of reduction in stress due to the initial arching modulus. When we get to the point of maximum curvature, we have even more reduction. And ultimately, we get to a point of minimum stress. Obviously a sweet point. However, in many cases, it's not going to stay there. With further deformation as a result of time-dependent properties of reinforcement and or subsoil, we're going to lose some of our arching effects. And we'll get load recovery ultimately to a steady state. To illustrate this, let's think about what's going on. If we have a dense sand, we have a pile, we have subsoil settling around it, it is really very much like a bearing capacity problem. Above the pile, we're going to get type 1 shear bands forming, where the major principal stress is vertical, and outside we're getting type 2 shear bands, where the major principal stress is horizontal. And in that case, we can get a stress reduction ratio that looks like this. In a less dense sand, it's more like a punching failure, and we get our type 1 shear bands, but it is much less clear that we get type 2. And we may get a relationship like this. To illustrate that, let's look at the effect of relative displacement for a dense and a medium dense sand on shear strain. So on the left we have dense sand, on the right we have medium dense sand, and on the extreme right we have a scale going from virtually no shear strain at the very dark blue to a lot of shear strain at the very dark red, with halfway between being a transition roughly green. And you can see if the relative deformation approaches about 1.5%, we're already starting to develop the type 1 shear bands. As we go towards 3%, you can see the type 2 shear band developing in the dense case, but not so clearly in the medium dense case. As we go to 5.5%, you can very clearly see the shear bands developed in the dense case, and the type 1 is very clear, but it's trying but not really getting there for the type 2. And here we are approaching 10%. Same story, very clear failure zone in and around the pile, but quite a difference for the dense and the medium dense cases as you move away. Now, why does this matter? Because many of the techniques being used assume the height of the failure surface is the critical height, but that doesn't always match observation. Since the failure surface is in fact a zone of high distortion, it's unlikely to be a plane of equal settlement. And in fact, recent research is showing that while the critical height, the plane at which you get more or less equal settlement, is related to the height of the failure surface, it is most certainly not, in general, equal to the height of the failure surface. So if you're trying to design for maximum arching, you need to ensure strain compatibility, which means the reinforcement stiffness must sag enough to generate the maximum arching stress, but not too much. Thus, while the reinforcement must have adequate stiffness, it also has to have the strength. Both are important, but stiffness is absolutely critical. So if we're looking at long-term serviceability assessment, we have to think about how long does it take to actually develop working conditions. Currently, limit equilibrium methods using arching models are deformation and time independent. They can be quite useful for ultimate limit state design, but cannot be used for serviceability assessment. Short-term performance is not necessarily a good guide to long-term serviceability. And what we really need to do as we move forward in this area is pay more attention to longer-term deformations due to creep of both the foundation, soil itself, and of the reinforcements commonly used, to really learn from what we've discovered with respect to embankments on soft soil over the last 40 years. So that brings me to the end of my last topic, a few conclusions. Reinforcement in embankments only plays a significant role when you have significant mobilization of strength in the foundation. The combined use of bearing capacity and limit equilibrium tends to work well for limit state design, the ultimate limit state, but care is needed to select the right shear strength, particularly for rate-sensitive soils. The finite element model gives us good correlation with observed behavior with appropriate model and parameters and provides insight regarding that behaviour. For embankments on peat, reinforcement can reduce lateral deformations, it can increase stability, but it does nothing much for consolidation settlements. We have to keep the pore pressures typically below about 33%, 34% of the total stress to minimise the risk of failures. And we find that effective deformation and strength parameters combined with pore pressures provide very good agreement between calculated and observed behaviour. On rate-sensitive soils, I'm talking about soils where the pore pressures increase after the end of construction, reinforcement strain can increase significantly even though the fill height has not changed. For a given embankment height, a stiffer reinforcement can reduce creep in the foundation. And the most critical time is with respect to when those pore pressures reach a maximum value, which is when you have minimum effective strength in your soil. And the strength from the laboratory and field testing both need to be evaluated very critically to consider what will be the mobilised strain in the field and what is a real operational strength. For floating column-supported embankments, the inclusion of basal reinforcement significantly reduces the stress on the subsoil and largely decreases the differential settlement between the pile and the subsoil. PVDs with reinforcement make things even better, and stress relaxation or creep tests are useful for giving insight into material behaviour, but need to be fed into an appropriate model to predict what's going to happen. Lastly, for end-bearing column-supported embankments, many advances have been made, but there are still challenges, particularly with long-term serviceability. We need to pay attention to both the time-dependent performance of the foundation and the reinforcement. So in the last 47 minutes, I've covered a lot of ground. It's been based on a large number of full-scale field case studies, sophisticated laboratory research, and advanced numerical modelling. Based on all of this, I come to three basic conclusions. First, soil reinforcement has been proven to be a cost-effective alternative to or augmentation of traditional construction methods. Understanding the properties and characteristics of geosynthetics is critical to success, combined with appropriate design. And don't forget the soil mechanics. The issues about time-dependent soil behaviour and of arching are all fundamental soil mechanics issues. I'd like to acknowledge a number of groups and people who've helped with the work that I've been reporting on, and particularly thank Tensar International for sponsoring this lecture. And I thank you for your attention. If you're interested in more, you can go to my webpage or send me an email, and I can send you the references or papers. So I wish you all a very enjoyable evening, and thanks for your attention.
Well, thank you, Professor Rowe, for a very understandable and nice lecture. I have a few parting announcements for this evening that Brad has asked me to pass along. Continuing on the theme of GSPs, cards with instructions for assessing the proceedings were inserted into your programs, and if you've lost that card, drop by the registration desk and they will tell you how to get your proceedings. Tomorrow we're going to have another set of poster sessions following today's very successful event, 3:30 till 5 o'clock in the North Star Room, again on the second floor. Tomorrow morning, we're going to kick off with the plenary session for the 68th Minnesota Geotechnical Society Conference. Lies Lalui is going to deliver the 2020 Kirsten Lecture, and also followed by a talk from Peter Kundal. And the Terzaghi Lecture tomorrow at 5:30 right here in this room. The lecturer for this year is Professor Ed Cording from the University of Illinois. I'm sure you're all rushing off to the Purple Party, the tribute to Prince. If you have gotten a ticket, please attend. It's important that those tickets be utilized. Reminder that you need a valid ID showing that you are 21 years old to attend. It's only 7 blocks away, but buses will be departing from the hotel lobby starting at, well, it said 7, but I've been assured that they'll really start running at 7:30. And there are still autographed pucks available at the booth, and they've been signed by Dave Christian, this morning's speaker. And you can also get more information about joining ASCE and all of the wonderful benefits that you get by being a GI member. So drop by when you have a chance to, and I hope to see you at the Purple Party. Good night. See you again tomorrow morning.
I get delirious, never